Welcome to The Explainer. Today, we're diving into a really fascinating and kind of radical new idea in cosmology. It's a framework that suggests the biggest puzzles out there, things like dark energy, aren't actually problems we need to solve with new particles. Instead, they might be huge clues that we've been using the wrong map of reality this whole time. So let's just jump right in with this central, provocative question this new model asks. What if the accelerating expansion of our universe, something we've chalked up to this mysterious dark energy, isn't real? What if it's just a geometric phantom? Now, to really appreciate just how different this new perspective is, we first have to understand the challenges that the standard model of cosmology is facing right now. And this is the model that, for decades, has been the absolute bedrock of how we see the universe. You see, as our telescopes get more and more powerful, the cracks in that standard model are getting a lot harder to just, well, paper over. To patch these things up, we've had to invent these mysterious placeholders, right? We've got dark energy to explain why the universe's expansion is speeding up, and dark matter to provide all this extra gravity we seem to need. But even with these patches, major tensions just keep popping up, like the famous Hubble tension, where our best methods for measuring the universe's expansion give us two different answers. It's a real problem. And this is where this new framework comes in and proposes a pretty radical idea. What if the problem isn't what's in the universe, but the map we're using to understand it? The whole idea here is that maybe we aren't missing new substances at all. Maybe we're just using a flawed geometric container, our familiar 3D space with time flowing forward, to make sense of all the data. At the absolute heart of this framework is a really powerful metaphor for reality itself. It's all about the difference between the true underlying structure of things and the version of it that we can actually see and measure. Okay, so the framework starts with this foundational idea, a four-dimensional reality it calls the counter space. This is the ultimate territory. I want you to try and imagine it like a solid block, where our past, our present, and our future all exist at the same time, just like different locations on a map. From this point of view, the flow of time that we all experience isn't some fundamental property of reality, it's just us moving through the map. So if that's the territory, then what are we? What is our universe? Well, it's described as just a geometric projection of that 4D reality. It's a map, or maybe a better word is a shadow. All the physics, all the things we see, are just one slice, one particular perspective of that deeper, static 4D structure. All right, let's break down the four axioms. These are the basic rules of this new map. First up, the whole content. Just like we said, reality is a static 4D block, and our experience of time just emerges from that. Second, identity of source. This one proposes that all singularities, things like black holes, all share a common origin point back in that 4D space. Third, shadow realization. This just means our 3D world and all of its physical laws are a direct projection. No funny business. And finally, and this is really the key insight, parsimony. It says that those dark effects we've been chasing for decades, they aren't new particles. They're simply geometric artifacts, distortions created by the very act of projecting a 4D reality onto a 3D map. Okay, so let's see how this framework reinterprets what is, I think we can all agree, the biggest puzzle in cosmology today: dark energy and the accelerating expansion of the universe. The standard model, right? It pictures dark energy as this mysterious fluid that's pushing everything apart equally in all directions. Physicists call this isotropic. But this new framework says, hold on, there's another way to look at this. It suggests the acceleration we think we see is an illusion, an artifact caused by our 3D map being sort of tilted or viewed from a particular angle within that bigger 4D territory. Now, a fluid can't have a preferred direction, but a projection absolutely can. And that would mean the acceleration isn't uniform at all. It's directional. And here is where it gets really interesting. There's data that seems to back this up. An analysis of supernova data actually found that the cosmic acceleration isn't uniform. It looks like it has a preferred direction, with a statistical significance of, get this, 3.9 sigma. Now, in science, that is a very strong signal that something real is going on. In fact, that same study found something pretty mind-blowing. Once you account for this preferred direction, the evidence for a universe-wide acceleration nearly vanishes. It becomes statistically consistent with no acceleration at all. Think about what that means. It implies that the whole dark energy effect might just be an illusion, something we created by averaging out a directional phenomenon across the entire sky. So, okay, if dark energy is just a geometric illusion, what other weird stuff can this new map explain? Let's take a look at how it handles some of the other major puzzles that have really stumped cosmologists for years. So one of the biggest ones is called the radio dipole anomaly. Here's the deal. The cosmic microwave background, the CMB, it's like an anchor for the whole universe. It tells us we're moving at about 370 kilometers per second. But when we measure our motion relative to a bunch of distant radio galaxies, we get a completely different answer, and it's much, much faster. Yeah, this chart really just lays the problem bare, doesn't it? The CMB, the afterglow of the Big Bang, suggests our solar system is cruising along at about 370 kilometers per second. But then you look at our speed against a backdrop of distant radio sources, and you get a number more than 4 times higher. In the standard model, these two measurements, they should agree. And they clearly don't, not even close. And we're not talking about a tiny measurement error here. This discrepancy has been confirmed at a confidence level of 5.4 sigma. To give you some perspective, in particle physics, 5 sigma is the gold standard for claiming a new discovery, like finding the Higgs boson. So when you see a 5.4 sigma problem, it's a huge red flag that something in our standard picture of the universe is fundamentally wrong. Now, this is where it gets really elegant. Standard cosmology just assumes distant galaxies are scattered randomly across the sky, kind of like raindrops on a sidewalk. That's a pattern called a Poisson distribution. But if you look at the Poisson fit column, you can see the numbers are really high, which means the data doesn't fit that model well at all. It fits much, much better with a different statistical model, the negative binomial distribution, which describes things that are clustered together. And this framework has an answer for that. It says, of course they're clustered. They aren't independent points in our 3D space. They're the projected shadows of structures that are actually connected in the 4D counterspace. And what about the famous Hubble tension? Well, this framework suggests it comes from the exact same core issue. We're trying to apply a single uniform expansion rate to what is actually a complex folded 3D projection. I mean, think about it. On a curved map of the Earth, the distance between lines of longitude changes as you move. Of course, the rate of expansion would seem to vary depending on where you are and which way you're looking. So, what's the big takeaway here? What does this framework imply for the actual practice and future of physics? Well, it's proposing a pretty fundamental shift in what our goals should even be. And this really brings us to a profound shift in thinking. Instead of hunting for invisible dark particles to try and patch the holes in our theories, this framework suggests that physicists should become cosmic cartographers. The goal isn't to find new things anymore. The new goal is to accurately map the higher dimensional reality by studying the distortions, the anomalies, and all the statistical clues that are already right there in our data. We just need to map the features of our 3D shadow. As the author of the paper puts it, and I think this quote really says it all, the dark sectors are not substances that are waiting to be discovered in some particle accelerator. They are geometric truths that are already present in the data, just waiting for us to correctly map them and understand what they're telling us. So in the end, this framework presents a really challenging and, for me, a very exciting new way of seeing the cosmos. It's asking us to seriously consider whether the universe we observe, day in and day out, is not the final territory, but maybe it's just a complex, beautiful, and sometimes very distorted map of a reality that is far deeper than we ever imagined.